So mixed emotions, I started thinking about mixed emotions about 20 years ago from a decision-making perspective in terms of gains and losses. And then I had long conversations with Dale Griffin. At that time, he was working on attitude ambivalence. And he's talking tomorrow. He'll talk about some of that work. And then I put it aside for a while, and then when I started collaborating with Jackie Smith and her group, Lindsay, Ryan, and a few others, I came back to this sort of topic of mixed emotions. So I'm going to approach it as a methodologist more in this talk than a psychologist. We've had lots of examples today. We know that retirement or major life transitions provide one opportunity in which to experience mixed emotions. So Larry King, when he retired, said the bittersweet feeling of saying goodbye. Now, what we're doing in our work is we're trying to see if there are also mixed emotions in everyday activities, right? We already know that in major life transitions there are mixed emotions, but what about in everyday life? In some of the analyses that we've done on a couple of different data sets, we find patterns like this. These are all older adults, 51 and greater. And the three bars reflect the proportion of the sample who endorsed only positive items on an activity, such as working, in this particular case, it's activity on a computer yesterday. 0.6% of the people mentioned only negative things, but 43.5% mentioned both positive and negative about their experience yesterday on a computer. Right? So an example might be they were very positive to be able to Skype with their grandchildren, but then they also had frustration because they couldn't get something to work or the screen froze on them and so on. All right? Similar things with activities such as TV watching and just global ratings of yesterday. How did you feel yesterday? Happy, sad, angry, fear. And we also find a similar pattern. The people who claim only negative in this sample is very, very low, the percentage. The highest is always the positive, as you've seen in these cases, but mixed is somewhere in between. So if you want to study negative emotions, you're not going to be able to do much with only looking at negative, right? The mixed is an opportunity to study negative emotions. Now, as we heard today, there are lots of different issues. Is it a set of basic emotions that get combined? Is it a simultaneous experience, or do we switch back and forth? And so on. We talked about age gradients. As the more I get into this multiple emotions literature and thinking about how to model it, the more difficult it turns out being. It's not something I anticipated. I thought it would just be a very simple problem to solve. But what I want to do in the rest of the talk is give you some of the intuitions of some of the directions that we're going in terms of trying to come up with models and ways of staying true to the phenomenology of a mixed emotional experience. What we don't have, so we do not have these things. We don't have a good theory about mixed emotions. We don't have good models, and I don't think we have a very good scholarly understanding of the phenomenon of mixed emotions. I think we've experienced it, and we can sort of speak as experiencers of multiple emotions, but as scholars, I don't think we have a very good language yet. Right? We don't have very many words besides bittersweet and poignancy to capture the experience of mixed emotions. But we do have lots of datums. And so with all those data that we have, there's lots of things that people have done in the literature. One of the more common ones that I like is just simply to count the number of times in which both positive and negative were endorsed. This has the problem that it ignores the intensity, but just as a simple count, to be very simple, you had to experience both positive and negative regardless of degree. So if you didn't experience any negative or you didn't experience any positive, then that doesn't count as mixed emotion. Our group with Jackie Smith, Lindsay Ryan, and others, we've extended that definition to multiple activities over the day. So we have a paper that came out in 2014. We introduced a measure called activity affective complexity, which is basically this count measure that I just described, but over activities for the day. So the percentage of daily activities in which you experience a negative emotion. Just to recap from what you saw this morning, if positive and negative are scaled on a 5-point scale going from 0 to 4, this is the space of all possible points that you can observe on positive and negative. And so this count measure that I described basically only looks at the blue region. So if the data point falls in the blue region, it counts as mixed emotion. If it falls outside the blue region, that means there was no negative, some positive, or some negative and no positive. Those are the clear regions. So those don't count under that measure. And here's a graph from one of Jeff's papers. Here are the clear bars in the exterior of the perimeter are cases where there are no mixed emotions because it was only positive or only negative. And the black bars are cases that count as having shown mixed emotion because there's at least one negative and at least one positive, right? So we are working on a three-dimensional space here. And this is useful for what I'm going to be doing very soon. Now, we can add intensity to this notion. So while the count measures is nice, we can sort of take the proportion of times in which an individual expressed both positive and negative. But we can add intensity to that. And this is what some of the measures we saw this morning try to do. One of the measures is the Kaplan measure. And rather than just give you the measure the way it's used, let me derive it for you quickly. The logic is that you take two concepts. So this is actually a two-factor model, conceptually. One is the intensity of positive and negative, and the other is polarization, the discrepancy between positive and negative. So if you take the difference between the sum of positive and negative on the one hand and the absolute difference of positive and negative on the other, if you take that difference, that's the Kaplan measure, which just ends up being equal to the minimum of the two. Whichever is smaller, positive or negative, that's linearly related to this measure, right? But I think conceptually it's good to have this notion of intensity versus polarization because it'll be very useful in a couple of slides. Here are examples of different intensities. So when the minimum is 1 versus 2 versus 3, the region that captures the mixed emotion at that threshold gets smaller and smaller. All right, so let's build this idea of intensity and polarization. So we start off with positive affect, negative affect. Those are two axes. And I'm suggesting, as many others have said, that maybe we could talk about two different axes, intensity and polarization. It turns out that they're related to each other just by a simple rotation of 45 degrees. So we saw this in a couple of slides this morning with the circumplex. Here it is from one of Cassiopo and one of Cassiopo's papers, where the original axis is positive, negative, but if you just rotate the axes 45 degrees, now you have one axis that's bipolar or polarization, and the other is intensity, which is the sum or the co-activation of both. Okay. If you now go through the literature and start cataloging the measures that have been proposed, the Kaplan is the first row, and that's, as I said before, this is equivalent to the minimum of positive or negative, linearly related to the minimum. There's a measure that Dale proposed with his colleagues Thompson and Zana, which is just a small variant of the Kaplan measure, right? Instead of taking the sum of the two, positive plus absolute value of negative, you take the average of the two. And then there's variants by Scott and many, many others. There's dozens of these that have been proposed. But I've re-expressed them in two columns. One column being intensity, which is some measure of positive and negative together. And then a second column, which is the polarization, which is some measure of discrepancy between positive and negative. And the little details just are peculiarities to that unique measure. Now, each of these create contour curves. These are regions of equal height, because remember, this is really a three-dimensional space. It's positive, negative, and then the ambivalence value is the third axis. So instead of doing three-dimensional plots, I'm just doing contours. And you'll see that the Kaplan measure has a very simple order to it. we saw this earlier in one of Jeff's slides, where you showed where all the ones are, where all the twos are, where threes are, and where the single 4 is in the upper northeast corner. So the Kaplan has that sort of property of indifference curves or contour curves that are linear with constant slope. The Griffin measure just changes the slope a little bit. They're still parallel. So going from here to there at all the different levels, they're parallel to each other. The other measures introduce some nonlinearity because now these indifference curves have some curvature to them. And there are several ways in which this is helpful. These kind of plots are helpful in choosing your stimuli for what experimental studies you want to do, because there are some regions where two theories might make very similar predictions because they have contour curves that look very similar. And there are other regions of that space where the two theories have sweet spots where they make different predictions on the contours. And that's maybe where you should be honing in your experimental studies, is specifically on the regions where the theories make differential predictions. If you just try to focus on the gestalt, the global space, it would be very difficult to compare these different indices to each other. Right? So designing studies is one approach, or one helpful use of these kinds of displays. The second is that it might guide our theoretical work. So we can define at a point, positive and not positive negative space, the slope of that indifference curve. And the slope of that indifference curve is basically a ratio of two partial derivatives. And it turns out that in the early days of mathematical social science, if you go back and look at the early work of, for instance, Herb Simon, this is the way they expressed hypotheses. So if you think that the ambivalence measure should increase as both positive and negative increase, the ambivalence measure should increase as the smaller a p or n approach the larger. And then you think it should decrease as the larger a p or n increases. That ends up putting constraints on the slope of these indifference curves or these contour curves. And this leads to testable predictions. Right? So instead of building an index by saying, I think I'll take my columns of data and start manipulating them, what you do instead is start off with process language about what you think is going on. And once you are able to list those processes, then you see what constraints they impose on the slopes of the contour curves. And then you can derive the index that corresponds that would produce those contour curves. Right? So you're going in a different direction from deriving the indices. You're starting off with psychological theory, if you're a psychologist, and then seeing what constraints that applies on the slopes, and then you go out and collect data and see what index corresponds to those predictions in the slopes. Those of you that heard me talk before know that I like functional equations. It's a small area of mathematics that most people don't know about. The basic idea is that it lets you solve for unknown functions. So similarly to high school algebra, where you learn how to solve for unknown variables, functional equations is unknown functions, right? So if our unknown function is ambivalence, we can use functional equations and see, well, how can we derive an index that captures the intuition of what we mean by ambivalence? So there's an important property that gives rise to a difference between intensity and polarization. So if you think that it's important that your index have this difference between intensity and polarization, that's what the index should give you. But you're open to the arbitrary function of the difference. You're just looking at the difference between intensity and polarization only up to a monotonic transformation of the difference. It turns out that this property of translational symmetry is necessary and sufficient to give you this representation. And the property is very simple. The property says, if you have a particular intensity and a particular polarization, if you can conduct a study where you could increment intensity by an amount k, and in a different condition, decrease polarization by the amount k, that you should have equal ambivalence in both. And you can see if I'm adding something to one thing and subtracting something from the other, and then I take the difference of those two things, the k's will cancel. And so if you find an experimental manipulation in which you, or a paradigm in which you can test this property, and you find that it fails, you show in your data that this does not exist, then in that one demonstration, you've eliminated all indices that make use of intensity minus polarization. Not just ones that exist currently, but any future indexes somebody might propose. If somebody says, I have a new index that takes a difference between intensity and polarization, you can instantly say, stop, don't waste your time. We know that translational symmetry doesn't work, and so whatever ambivalence is, it's not a difference between intensity and polarization. So this is a very powerful way to do math modeling in our sort of social science world. As I was working on this, I noticed that prospect theory can also be expressed in intensity and polarization. So prospect theory is a very important model in decision-making under risk and uncertainty. And basically, if we have outcomes, X and Y are two outcomes, say $100 and $50, and there's some probability that we get the 100, one minus that probability that we get 50. Prospect theory is written this way, which basically says weight the 0.5 times the value of getting 100, 1 minus the weight of 0.5, the value of getting 50. But if you rearrange the terms, just using high school algebra, you get an expression that's just intensity, a function only of the sum of the two outcomes. This is basically the Dale Griffin part, right, where he took the Kaplan and had the sum, and then you divide it by 2. And then over here we have an absolute value of the difference between the two outcomes, weighted by the transformation of 0.5. So prospect theory has this sort of ambivalence built in. But the weird thing about this that I haven't been able to get my head around yet is that this only works for same valence gambles. So both outcomes have to be both positive or both negative. This is what prospect theory says. So prospect theory says that you experience ambivalence in this general definition of intensity minus polarization when you have same valence outcomes. But when you have different valence outcomes, which is what most of us mean by mixed emotion, right? Positive and negative together, a gain and a loss. It turns out that prospect theory only has the polarization part. And to me, that's very counterintuitive. I would have expected the mixed gamble to have the intensity minus the polarization. But I'm stumped on this one. So if anybody has ideas, I'd love to hear. Okay, I can skip that, and I'll skip that. Some other statistical approaches that people have mentioned earlier today and also in the literature are variance-based approaches, correlation-based approaches, and dimensional approaches. And these basically correspond to different ways of decomposing variances, different ways of looking at the correlation between positive and negative, right? So earlier we heard that some models of mixed emotions would imply a perfect negative correlation between positive and negative and so on. And the dimensional would be people who take a correlation matrix involving positive items, for instance, and they start counting up the number of principal components that have an eigenvalue greater than 1. And so if there's only 1, that means you don't have much granularity. Your positive emotions just all kind of correlate equally. If you have many factors for the positive emotions, it means that you sort of differentiate the positive because you have these different factors. Some of the problems that are present in these things is that people that do these number of eigenvalue analyses don't seem to care much about the particular factor structure. So you might have one eigenvalue greater than 1, so you're a one-factor person. I might also have an eigenvalue greater than 1, so I'm a one-factor person. But both of us might be have different factors. And in this measure, that completely gets ignored because we both get counted as one-factor people. And there might be some interesting psychology in the individual difference of what our one-factors look like. Also, all of these measures, these variance, covariance, and decomposition measures, they're all related to each other. So if you look at these correlation matrices, a lot of them have values that are very similar to each other, like in the 0.3 range or in the 0.4 range. So if you just basically say, all right, all the correlations for all the positive items are roughly in the 0.4 range, you already know what the value of the first eigenvalue is going to be, and you know what all the other eigenvalues are going to be. I've just given you enough information when I tell you that the correlations are all about 0.4. The first eigenvalue will be the number of positive items minus 1 times 0.4 plus 1. That's the first eigenvalue. So you can see that what drives the first eigenvalue is the correlation. So these are transformations of each other. And I know in a lot of literatures that I've been reading, people will try all these different approaches and put them in as predictors, but they're really all transformations of each other, and so it's just a mess. The U index is something that's now become popular. This is basically the proportion of the day in which negative is greater than positive. Right? This happens relatively infrequently in the samples that we've looked at. Most of the time, positive is greater than negative, but this is a useful concept in some literatures. And then the 2 quick points, and I'll close. It's funny that the theory people were all on time, and the methods people are the ones that are all going over. So, all right. Calibration is a concept that we need to look at carefully. This is looking at self-reports of the experience of mixed emotion, comparing that to the indices that we create of separately collecting positive and negative. So if you can show a particular index might overpredict or underpredict the actual experience, you can learn from that to see where the index is going wrong, where it's going awry. And then the last kind of thing I want to point out is the other popular thing right now is to have a very complicated multiple regression in which to analyze mixed emotions. And so you start off by defining a dummy code W, which W codes 1 if positive is greater than negative, 0 if positive is less than negative. So it's a simple dummy code. And it's basically doing a more general model than a difference score. If you input it as your predictor, positive minus negative, you're imposing constraints on the betas in the regression. But by doing this little trick of the dummy code, you can now relax that constraint and test the difference separately from the main effect of P and W. So the full regression would be the 3 main effects, and the 3 two-way interactions between those variables. And now many of the indices that people have studied are just special cases of this more general model by putting constraints. So the Kaplan measure, for example, doesn't have any main effect variables. So beta 1, beta 2, and beta 3 are all set to 0. And then beta 2 and beta 5 are equal, and beta 2 and beta 6 are equal, but except for sign. And so now you can test in that general model that you run if the constraint of those coefficients fits the data. The problem with this approach is that you're creating the index at the same time that you're evaluating the prediction of that index on the dependent variable, right? So for one dependent variable, Kaplan's measure might work, and then if you try a different dependent variable, now the Griffin measure might work, or the Scott measure might work, because you're doing both the prediction problem on the dependent variable as simultaneously to testing the pattern of coefficients. So it'll be a moving target, right? For this paper, ambivalence might be defined one way, because that's one dependent variable, one set of covariates. And then for another paper that you write, when you might use a different set of covariates, a different dependent variable, and now you have a very different index. So that's not a great property to have in science if you want to be able to accumulate knowledge. I think you don't want to have a moving target in terms of your definition of the index. So I'll stop there. Thank you.